Hello, everyone, and welcome to the 2020 HPCC Virtual Summit. My name is Jesse Shaw. I'm your host and moderator for this session titled Data Lake Deep Dive with Roger Dev. Roger's a senior architect at LexisNexis and is responsible for the HPCC machine learning libraries. There will be a Q&A session, so please submit all questions through the interface. Roger will be answering the questions at the end of the presentation, but please don't wait until the end to submit them. So without further delay, I give you Roger Dev.
Hi, everyone, and thank you for coming back for more. If you saw the overview presentation, we'll go a little bit deeper in this presentation, but first I'm going to do a little recap in case anyone missed the previous session. So data lake is an architecture and methodology for continuous management of complex data. Data coming from many sources and many formats, and that has many use, and where you want to continuously extract value. If you think about it, the only reason for a data lake is to extract value, to add value to the data that you collect and provide additional value to your users. A data lake brings in external data, processes it continuously, again and again, refining and refining the data, and finally delivers it to a wide variety of external clients. We contrasted the database perspective with the data lake perspective. In the database, you have a final schema, which all of your applications use. In a data lake, you have data at every level of refinement. You store your source data, you store your various levels of refinement, and a final form for each individual application. Developers can then reach in to any piece of that data. If they like the analysis you've already done, they can grab it in the middle. If they say, no, I want to analyze it in a different way, they can go back to the raw data and do their own analysis. So it's very flexible and very powerful for dealing with complex data. And the problem with complex data is you don't know what the endpoint is. You can't build a schema that's going to reflect all of your needs, uses, and different analysis paths for that data. So in the overview talk, we reviewed the benefits of data lake, and I promised to talk about development efficiency. Recall that one of the hallmarks of data lake technology is the ability to scale. It can scale in terms of data volume and number of users, but just as importantly, can scale in terms of the development process. A very simple example will illustrate how data lakes allow many teams to develop at their own pace while avoiding costly dependencies. In our example, we start with two data sets. We then merge those data sets together to produce a composite data set. That composite data set is produced by a team in order to create the data needed for their application, which we call App 1. Now another team finds that data useful and builds another application, App 2, using the same already merged data. A bit later, App 2 team acquires a third data set and wants to upgrade their application to include that data as well. They can upgrade the transformation to include this data, but that would require App 1 to stop the unrelated projects they've been working on and analyze, retest, and repair their application so that it's not impacted by the change. This, of course, would force the App 2 team to delay their release until the App 1 team has had the chance to do this work. This type of dependency typically results in significant delays and cost overruns on both teams' projects. Data lakes offer a simple and powerful way to avoid such costly dependencies. The app2 team simply creates a new merged data set that includes the original merged data plus dataset 3. They can carry on with their project without in any way impacting the app1 team. At a later date, the app1 team may decide to do an upgrade and point their application to the second merged dataset as they make other changes. They can do this on their own time and without impacting the app2 team. This basic approach allows many teams to simultaneously develop and productize application changes without unnecessarily impacting one another. So teams may be using the data for some teams may be using the data for exploration, while others are deploying hardened applications. I'm going to look at data enrichment from a slightly different perspective, take you through a different set of examples, and provide some additional information. So complex data is characterized by an ever-expanding set of sources, each with their own imperfections, nuances, and hidden gems of value. These data sets are usually very large and constantly expanding in scale and volume of change. None of us are smart enough to look at such a body of data and know where the value is hidden. But nonetheless, we want to extract value from it and continually refine that data through discovery, extraction, and ultimately productizing the nuggets that we have discovered. In my overview talk, I took you quickly through the dimensions of data enrichment, and we're going to go through one more time in a little more depth, and this time I'm going to weave a common example through the entire process. So imagine that we run Acme Cab Company out of New York City. We have our own data regarding rides, the start time, end time, start location, end location, medallion number, and number of riders. We use this example as we look at the dimensions of data enrichment. The first and most obvious way to enrich data is by removing errors and inconsistencies. All sources of data contain these. For Acme, this refined data set may provide better insight into our operations and improve our decision process. Data anomalies can come in surprisingly many forms, from obvious errors like invalid values or missing data to subtleties that only show up during certain types of analysis. By adding statistical analysis, we can begin to see how a given day's traffic compares to typical usage. We can identify unusual flows and usage trends. We may be able to better utilize and allocate our resources and position our cars. Metrics for our taxi business might include things like riders per trip, idle time, trips per day, average trip fare, miles per fare, cab profitability. These can be helpful in understanding the state of the business and for making adjustments to the operation. But as the data lake expands, metrics will be developed for different types of users and for many different purposes. Coverage enrichment, you recall, is the process of adding more data sources for the same type of data. If we can include other New York City cab companies, that would increase the general value of our data. Suppose we can access cab data from Chicago and Los Angeles. What if we could include Lyft and Uber data? The closer we come to encompassing the full scope of the given data set, the more the value increases. Breadth enrichment is about finding data that is complementary to our existing data. Suppose we overlay GIS information about business addresses and other venues. Now we can begin to infer where passengers are coming from and going to. This starts to enable us to visualize flows of tourists and commercial activities across the city. Now we've begun to open the doors to prospective clients outside of the transportation sector. We could imagine many such overlays, such as a calendar of events in the city. Entity resolution can be a critical, yet very challenging type of enhancement. This involves translating tags in the data into a persistent identity. In some cases, this can be trivial. The medallion number of the cab has a fixed identity that may exist in the raw data. Often, however, entity resolution is much more difficult. What business is the rider going to, for example? Addresses may serve many businesses. Business names might not align from site to site. Sometimes entity resolution is definitive, but in many cases it requires statistical inferences. While these inferences are never 100% reliable, perfection is seldom a prerequisite for value extraction. Many businesses thrive by producing data that is more accurate than other sources can offer, even if far from perfect. Generally, the more breadth and coverage available, the better these statistical inferences can be. Relationship resolution looks at associations between similar or dissimilar types of entities. In our example, travel could be mapped between pairs of businesses or between transportation hubs and venues. This can also be challenging yet very rewarding. In some cases, entity and relationship resolution may need to be done jointly, as certain entities can only be resolved as a function of the relationships that they occur in. Relationship mapping can be taken a step further using transitive associations. This is following the chain of relationships to produce inferences about an entity. Think of the chain of the various rides that a person may take during a day and how that may illuminate deeper patterns in the data. Qualitative analysis is used to categorize or classify entities or relationships. Is this trip personal, tourism, or business in nature? In some cases, these can be handled through a set of simple rules, but often machine learning is employed to determine these qualitative attributes. Diagnostic analysis attempts to identify anomalies or other interesting conditions. Perhaps ride times can be used to indicate accidents or other disasters. Unusual spikes in usage might indicate errors in the allocation of vehicles. Finally, predictive analysis looks at time or space variant relationships. Are certain business usage patterns among rides leading indicators for future economic or market conditions? Can they indicate the need for enhanced police or traffic control presence? Various machine learning and analytic techniques can be used to model these subtle interactions within the data. You can see that with time, effort, and creativity, our modest starting data lake could soon eclipse in value the company that started it. Let's go back to understanding what is an enterprise data lake and why it's important. So an enterprise data lake, as we talked about earlier, must be scalable, resilient, and secure. It must be elastic in terms of its compute and storage. Must support both exploration and production hardened flows simultaneously. You don't want to have a shift and lift to go from your discovery of value and the realization of it for your customers. Must have minimal effort to transition from exploration to production. Seamless end-to-end process, transparent curation and governance, and interoperation with existing systems and processes. So there's some big challenges there that may not be obvious on the surface. People building an initial data lake often overlook the severity of these challenges and think it's just flat files, so I can use Hadoop and Python or Spark and I'll have a data lake. They underestimate the many factors involved in operating a data lake. Many types of users will be simultaneously using the data lake for exploration as well as production. And important security and access control procedures must be available. Nearly all reliable sources of external data include covenants or privacy concerns that must be carefully managed. As the data lake generates value that many users come to depend on, the expense of any kind of outage goes up dramatically. Users may demand service level agreements with requirements in terms of uptime, data currency, coverage, and accuracy. The system must be resilient against equipment failures, loss of data, and often overlooked data corruption. As the number of sources increase, the likelihood goes up that an error at one of the data providers can cause significant corruption in your data. It's critical to be able to detect and rapidly roll back this corrupt data. Imagine in a database management system trying to undo all of the cascading errors caused by a corrupt data feed that perhaps was not discovered for some hours or days. Ingestion and enrichment are continuous processes. As new data arrives, it must be ingested, analyses run, and final data produced within the window of currency required. If data cannot be processed at the rate it's produced, then the analysis can get further and further behind. In a system that requires major upgrades to increase capacity, this can be very hard to manage and requires much reserve capacity. A successful data lake will have an ever-increasing population of users that may grow faster than infrastructure upgrades can keep up with. We've talked about the need for curation governance. Without it, a data lake quickly devolves into a useless and dangerous swamp. Reusability and the ability to build on previous knowledge requires that the data transformation process and governance requirements are fully transparent. Finally, the data lake must tie into many of the same security and administrative systems used by other IT processes. So let's take a look at the components of HPCC and how those contribute to the building of an enterprise data lake solution. The system includes a data curation subsystem called Tombolo, which is just being released at a beta level, a single parallelized language ECL that controls the entire process, a rich library of machine learning and analytic methods, and fully scalable engines for data enrichment and delivery to end users. We'll discuss each of these in the following slides. Tombolo provides visibility into the data lake. It graphically depicts the datasets, transformations, access paths, and user queries for the entire data lake. Tombolo allows drill down into the details of each of these elements, all the way down to the transformations that generate each piece of data. It provides a repository of documentation, governance needs, and procedures that allows data to be located, managed, understood, and reused. It supports the entire process from design to production and simultaneously allows private exploration as well as production hardened flows. It tracks the progress of defined workflows and alerts appropriate parties in the event of a failure. There's a link down at the bottom here. If you'd like to try out Tombolo, it's available at that link. The Enterprise Control Language, or ECL, is a powerful data flow language that defines the flow of data from end to end. The declarative language, which means that you tell it what to do with the data and not how to do it. In other words, you define the nature of the data you want to produce, and the compiler figures out how to make that appropriate transformation happen. This is a very important distinction for a number of reasons. First, it provides a transparent specification of the transformation without any obscuring technical details. Second, it allows the language to automatically parallelize the actions across any number of nodes. Add this to the fact that ECL is transparently compiled into C++ code, and you have the ability to process huge amounts of data very quickly. Further, there's no need to worry about technical issues such as memory management. ECL will run in memory when it can, or automatically spill to disk when the data cannot fit in memory. ECL is transparent and easy to read and provides an excellent document describing the transformation required. ECL is a full-bodied transformation language with enough power to perform nearly any imaginable transformation. For example, we often implement parallelized machine learning algorithms completely in ECL. ECL also allows simple embedding of other popular languages such as C++, Python, and Java, allowing the user to use off-the-shelf analytical libraries written in those languages. HPCC provides a broad set of analytic and machine learning libraries that are parallelized and optimized to run on the HPCC platform. These include a wide range of statistical methods, natural language processing, supervised and unsupervised machine learning, neural networks, and image and video processing. These methods allow the incorporation of any type of data into your data lake and the extraction of structured information from unstructured sources. You'll see the link there to the documentation and code for the machine learning library. The Thor data enrichment engine provides a secure, highly performant infrastructure for iterative data enrichment. It's secure, flexible, and scalable, and incorporates many advanced features needed to operate a production data lake. It handles data flow from acquisition to final contents. Like the rest of the HPCC systems platform, Thor can run on a single laptop up to thousands of servers and in either an on-premise or cloud environment. It's fault-tolerant, able to handle processor failures or storage failures, and allows for incremental as well as batch processing. It provides mechanisms for automatic generational backups and recovery in the event of corruption of received data. Thor transformations are defined using the powerful ECL language, which is automatically parallelized based on the defined size of a Thor cluster. Thor runs the appropriate transformations based on workflow rules supporting manual, scheduled, and event-driven workflows. 3 different storage types are available to handle various real-world scenarios. Logical files present a unified view into files that are, in fact, distributed across the nodes in a cluster. Superfiles are powerful constructs built atop logical files that provide a unified view of multiple logical files. This provides ability for incremental processing of incoming data. New data is added to a new file, and it's virtually merged with other files as the data is read. Superfiles also allow for atomic updates, allowing for files to be written without impacting active users who are reading the same file. Data management provides automatic generational backups, supporting data reliability and the ability to roll back from data corruption errors as typically result from a bad feed from a provider. Thor also prepares the data for rapid access by the Roxy information delivery engine, including sophisticated indexing capabilities, allowing random access into the enriched files from any direction. The Roxy data delivery engine delivers data to end users or applications using the most popular query protocols such as SOAP, REST, JSON, or SQL. It provides a secure API management environment with fast response times and is able to support diverse user communities of any size with multi-way scaling. The front-end and back-end processing can be independently scaled as needed. Like Thor, Roxy can be run on any size cluster, on-premise or in the cloud. In the cloud, Roxy can automatically scale up or down to meet the fluctuating demands of the user community while minimizing costs. Roxy queries are defined using the same powerful ECL language as used by Thor, and the 2 systems interlock seamlessly. One button push causes the results of an ECL query to be published and available to users in one or all of the supported formats. Roxy is also commonly used for the real-time ingestion of data from Internet of Things devices that can then be enriched and made available to users. A new component that you may not be familiar with is called Real BI. This is also a beta level component, but it extends the reach of ECL out to the end user experience. Traditionally, ECL ended at the serving the data up to the end user's application. But with Real BI, you can create dashboards, graphics, etc., using ECL, or many dashboards don't even require any coding. They can be just put together from the data or queries that you've already created. But any customization is done in ECL, so that extends ECL's reach out to the end user experience as well. So we really do have a seamless end-to-end solution. So a user that learns ECL can now go from ingestion to analysis to serving the data to actually viewing the data without changing contexts. So that's my data lake overview. Now I'm going to go into a more informal piece of the presentation, talking about how to get started if you want to build your own data lake. Again, we think a lot of the industries of the future are going to be built on data lake technology, and they're going to be based on ingesting information from various sources and producing more and more value from that data. So clearly, the first thing to do is to choose a domain. Hopefully, that's a domain that you have some expertise in, but it's not always necessary. If you see an opportunity of any domain where you don't find information you're looking for, or you can't quite understand what's going on based on the information that's there, or you see ways that you could enhance that information, and that may be a domain to explore. Of course, you need to find some initial data sources. Often, you start with a small number of data sources. We recommend that. And then when you run out of things to do with those, you go search for other data sources. And sometimes it's surprising what other data sources can be complementary to the data source or to the domain that you're working within. For example, we found in the COVID-19 project that cell phone mobility data could give us clues into the movement of people and really the level of social distancing that's occurring within the location, which can help us to predict the evolution of the infection in a given location. Next is to find some key questions. These can be in the form of user stories, if you like agile development. But basically, these are things that you want to know that are not obvious from the data that you've been able to acquire. And build the causal model. You'll hear me come back to the causal model again and again and again. And there are a lot of reasons for that. It's the most useful way to understand your data in terms of the actual meaning of that data. And I'll get into some examples here. So this is a causal model that we developed for the COVID-19 project. And I don't want you to try to read it. It's too complex to digest all at once. But I want to let you know that causal models are actually quite simple in nature. They're attributes that may be either observable or non-observable. We show observable attributes as a solid box and unobservables or latent attributes as a box with dashed borders. The arrows can be read as directly influences. So the first two boxes on the left with an arrow between them indicates that case reporting policy, which is unobserved, directly influences the observed variable reported cases. That stands to reason. If you look in the center of the diagram, you'll see a key variable called active infections. We cannot observe this, so we really don't know its value. But we can see that it is influenced by a large number of factors. And in turn, it influences most of the variables that we can observe, including reported cases, reported deaths, and reported hospitalizations. Now, you might ask, where did this diagram come from? An academic paper? A text on epidemiology? In embarrassing truth, I pulled it out of my head. What did you think I was going to say? I want to prove to you that you can do the same, or almost any field that you would like to explore. The human brain is uniquely suited for processing causal data. In fact, that may be its primary function. Allow me to demonstrate. I happen to have some expertise in growing trees in the Rocky Mountains. I run a hobby tree farm in the Colorado foothills. I suspect few of you have that expertise. I'm going to ask you to consider a causal model for tree growth. Think about the factors that might influence the annual growth rate of trees. If this were a face-to-face meeting, I would have you shout out your answers. But I don't want to try that in this meeting. It could become pretty chaotic. So just think to yourself what those causal factors might be. If you have a pen and paper, write them down. Go ahead, do that now. I'll give you 20 seconds to develop a causal model. Okay. Chances are you identified water, nutrients, sunshine, and tree species as factors that would influence the growth of trees. You may have thought of things like insect and disease prevalence, wildlife damage, and slope orientation. In a few hours of consideration, you could probably create a model that rivals any that I could develop without needing to know much beyond our common human experience. Now, no artificial intelligence system that exists today could have done that, except by regurgitating an article where a human had already figured it out. Regardless of the subject, we have the ability to rapidly jump to a very accurate causal model. Causality is a rapidly developing science. We've learned more about causality in the last 20 years than in the entire history of science, but it's still in its infancy. I expect that in the next 20 years, it will emerge as a field built upon the foundations of statistics, just as biology stands anchored by chemistry and chemistry by physics. Modern causality theory provides the mechanisms for the limited discovery and testing of causal models and an algebra for causal reasoning. Causal reasoning is required to answer questions like why, for evaluating effects, and for answering counterfactual questions such as how fast would the tree have grown if we had applied more fertilizer? Statistics can provide no answers for these types of questions. Consider any decision that we need to make. We start by asking, what would happen if I did X? What about Y? how could that first step even be taken without an internal causal model that asks, what would happen if I intervened in the current state of the model by taking action X? We have to process a causal model in order to know what would happen. So enough of my causality spiel. I could go on for hours. But back to the issue at hand. The causal model allows us to understand what each piece of data means in causal terms. This allows us to know how to treat that data we have in order to produce metrics that have meaning attached to them. For example, in the COVID project, we were able to define a social distance metric as a change in the growth in reported cases and show that it's a valid proxy for the social behavior attribute in the model, the third from the left box right here. Unfortunately, I can't teach causal inference in the time I have for this talk, but I strongly encourage you to study this if you have the opportunity. These two books encapsulate much of what is known about causality today, and I highly encourage you to read them if you're interested in learning more. So back to our data lake. Sorry, these are the books. So you got to live with your data for a while. After you've ingested the data, you want to start to understand it. You want to start to understand it inside and out. Best place to start is with the data patterns. Data patterns created by Dan, and it's available right here, HPC systems data patterns. And it's usable from either ECL Watch or directly by calls to the library. And it will go through each field in your data, and it will show the mins, the max, whether you have blank values or not, whether you show missing data. It'll show the distributions of the data if it's numerical. And it really starts to give you insight into your the structure of your data. Dan Kemper has done an excellent job with this, and it's very, very useful first step. So keep exploring your data. How reliable is it? Where are the errors? Can you fix those errors? How do you want to fix them? And the next step is you want to chart some of your data. And I recommend the visualization bundle. If you go to our GitHub site, the visualization bundle allows you right through ECL Watch to create graphs and look at your data, create graphs of almost any type. Then look at your data and relate it to your causal model. Go back again and again to your causal model and understand how your existing data relates to it. Does it tell you anything about your key questions? Examining your causal model, what would you need to know to be able to answer some of your key questions? Can you estimate those answers from the data you have? Are there other sources of data that would let you answer them? Once you do find a nugget, build on it and come back for more. I can promise you there are many, many nuggets to be discovered in any given set of data. And these nuggets, of course, are opportunities to add value. If you get stuck and you can't think of anything else to do with your data, and that does sometimes happen, add another complementary data source. And suddenly you'll find that opens up whole new avenues for exploration. Or expand your domain. Maybe your domain focus is a little bit too narrow. Maybe you want to open it up a bit more, ask different types of questions, and continually revisit your key questions, particularly the ones that you haven't yet been able to answer. So in closing, I want to emphasize the proven nature of data lake architecture. It's in use across a wide range of industries around the world. It's used by prominent information providers and large and small enterprises alike. Implementing and operating a data lake is not a trivial matter and requires substantial technology and expertise to be successful. HPCC Systems provides the most complete system for the creation and operation of data lakes. It's time-tested, secure, highly performant, open source, and free. Easy to install and get started. A single system download can be up and running in minutes. And it's available on our website, hpccsystems.com. I thank you for taking the time to attend, and we do have some time left for questions.
Hey, thanks, Roger. We have one question. At the beginning, you talked about how a data lake can actually supply data at various stages of enrichment. So John Meyer wants to know, how do developers discover those various stages of enhancement? How would you go about it? And maybe you just covered it with the exploratory data analysis you talked about with data patterns, but can you elaborate on that?
Yes. So typically the value of data is built up in layers. You've got your raw data, you've got your first level where you start to normalize that, bring your data sources together. So you typically will have a normalized view of your multiple data sources. Then you'll start to do some basic statistical analysis, add those into another data set. And finally, you'll develop more and more sophisticated, higher level analyses. And ultimately, you'll have layers of data that are specific to a given application that produce the indices needed for the rapid access through Roxy, that provide the access paths that you actually want to expose, and that refine the data for display to the users. So these layers are what you're typically going to drill into. Now, in terms of finding that data within a data lake, can be kind of daunting if you're just looking at a list of file names. But with Tombolo, curation system, it really makes that quite easy. With Tombolo, you can describe all of your data sets, what they mean, how they're used, what the restrictions on them are. You can define each field in the data set and what its meaning, what its usage, what its provenance is. And so that really increases the visibility of the data within your data lake and makes it much more accessible to developers that want to dive into an existing data lake and start working on their own ideas.
So that's great. Tombolo is new to me. Would it support multi-tenancy? Is that what you're saying?
Yes, Tombolo supports multiple projects, multi-tenancy. Provided a user has access to the data, they can get at the data. They can mark data as experimental or production, so that you may not want to build a application using experimental data because it's likely to change. But once a data set has been put into production, then you can feel free to use that data set to build your own applications.
That's fantastic. So are there any other questions out there? We have a few more minutes. We can post the Tombolo link in the public chat, or if you could bring that back up so everyone can see that. Logging in and registering was very easy. I did that as you were talking because I was excited to see what it was. If there's no other questions, Roger, thanks so much. All the other attendees, if you wanted to continue down the data lake path, Vince Free from North Carolina State University is going to be talking about making an agricultural-based data lake. So, Roger?
Yes. And next up is the COVID-19 data lake. You might find that talk very interesting.
Oh, absolutely.
Yeah, that's coming up in a few minutes here. And I want to thank you, Jesse, and thank you, everyone, for your time and attention.